So I want to start by giving you some examples of machine learning applications so that we're on the same page about what I mean by a machine learning application, okay? So here is a real world machine learning application. You can open your browser right now and hit this website. It's called NDA-LIN, and the idea is, should you sign that non-disclosure agreement? This is a question that I'm personally faced with very often. And you can just take your NDA, the actual text, and you drop it on the website, and it uses machine learning to decide if the terms are fair, and it comes back and says, well, you really should be concerned about paragraph 3, line 2 here, it doesn't look right. And this term here isn't, bi-directional fair and all this kind of stuff. And that's pretty super cool stuff, all right? But it's a complete seamless package. Website, drop file, get answer back, okay? And it does all the magic under the hood. There's actually a paper, if you go to that website, there's a link you can go to, and there's a paper where he describes how the algorithm works, which is pretty cool too. Pre-series is one that BigML is a bit closer to, but the idea here is we gather over 500 features about companies, from Crunchbase or tweets or patents. Just imagine all the public information that's available about companies. There's lots, right? And you create a label for success or failure over the history. Look at companies. Did they IPO or get acquired? We'll call that success. Did they go into bankruptcy or linger in irrelevance, shall we say? We'll call that a failure. And then we just build a giant model that predicts the success or failure of all the startups that are currently on the market. And we basically have like a little mini VC in a box. Okay, that's wired into all of the data that's out there about these companies. Okay, and this is a publicly available, well, not publicly, you can sign up. That preseries.com, you can go there and you can see this application live. Okay, and it puts this all together into a nice dashboard. It actually does a bunch of other cool stuff too with clustering and finding companies. So you can say, this is a company I like, and it'll show you a bunch of other companies that are similar and things like that. Yep. Okay, so this stuff exists, it's out there. Those are machine learning applications, full stack, end-to-end machine learning. Okay, ingestion of data, some kind of cool thing, and then a nice dashboard in the output. That's what we're talking about in machine learning application. So why is the machine learning adoption a little, still? I mean, it's like 10 years ago, there was an article I remember that was talking about, machine learning adoption is still not here. And I'm like, it's 10 years and it's still not here. Where is it? And so the gap for most companies isn't that machine learning doesn't work, but that they struggle to actually use it. This is in the Harvard Business Review. And my question to you, of course, is why? And my personal feeling is that there's been too much focus on algorithms, okay? Not enough focus on applying machine learning. What do I mean? Here's another good example. So this is a real-world machine learning application. This is Francisco tweeted this. The reason you aren't feeling as much turbulence. Now this article explains how this works. Let's read the explanation, all right? Collecting and analyzing hundreds of thousands of data points with a plan to boost that to millions, create a model that forecasts turbulence with a level of confidence heretofore unseen. And the thing that I really want you to focus on there, it says creating a model. That's it. It doesn't tell you anything about that model, okay? Because the really important thing in understanding what this does is this is the most irrelevant part of that paragraph. It's the most irrelevant part. Nobody cares if that's an ensemble or a logistic regression or a neural network, okay? And I guarantee you that's not where they spent their time. This collecting and analyzing hundreds of thousands of data points with a plan to boost that to millions, forecasting turbulence. I mean, those are the big problems they had to solve, right? What model they use is meh. Just the one that worked, okay? Look, this machine learning algorithms are really fun to talk about, right? I got my quad GPU and my TP processors, and I'm building these neural networks and stuff. But the algorithms are largely a commodity already. The algorithms themselves are already a commodity. The difficulty is knowing what you're going to do with it. How are you going to apply this machine learning? What are you going to do? Okay, so let's go back to that machine learning definition I gave you earlier, right? Where you have this flight data, we were going to apply some algorithms to get some predictive models, and finding patterns in data that can be used to make inferences. And when I told you that, you were probably like, yeah, hopefully you were thinking you had some data and you were going to go find some inferences, okay? And then maybe you start to think about, wait, where does this data come from? How do you know what data? What data are you going to collect? Is the data formatted correctly? It isn't. Let me just save you the suspense. What are you going to do with these models, right? How do you combine them? Will it work, right? Those are all the things that you're probably not thinking about yet, Okay, and they're the very first things you're gonna have to think about when you actually wanna do this. So here's the reality of machine learning application. There's some really fantastic predictive application, and it's sort of, the classic seen and unseen. It's the iceberg, okay? Underneath this really cool predictive application is all this feature engineering and data transformations and all this evaluation and retraining you had to do and all the data collection below all that, okay? And that's the stuff that nobody ever likes to talk about, right? It's like the dirty secret. Well, I'm gonna talk about it though. I'm gonna help you right now. Okay, so let's talk about where you're gonna start. So let's predict customer churn, right? This is a nice dovetail into the examples earlier. And that's step one, just knowing what you wanna do. And down here's the finish. Here are the customers we predict will leave our service. And my question to you is, what is step two? What is step two? Okay, well, let's detect fraud. Okay, here are the transactions we should stop immediately. What is step two? Is it decide whether you're going to use a neural network or a logistic regression? No. No. Okay, you need to state this problem as a machine learning task. That's the very first thing you're going to want to do. So remember that machine learning finds patterns in data that enable predictions about future events. Okay? This means you need data. And what data depends on what you want to predict. Okay? The data has to be able to have an inference about the thing you want to predict. You cannot collect data about, ice cream sales and make a prediction about the stock market. Okay, it's probably not an inference in there that's going to work. I could be wrong, but that'd be a cool model. Okay, and the data you have or can collect is also important. It might just not be possible to get the data you imagine. I still have this really cool stock market project, but I just can't get the data for it, by the way. Okay, so your data needs to have these patterns. They have to be related. So it's not magic. It still can't predict random events or lotteries or things like that. Okay, there's chaotic systems, although you actually can do a little prediction in chaotic systems, but for very short time events. Okay, your problem statement needs to be very specific, not let's predict churn. Okay, that's a great place to start. That's a goal. But let's predict churn by looking at the profile data of all the previous customers of our service who have or have not churned. This is a fantastic problem statement because now you know exactly what data you're going to get and how you're going to label it. You're going to get the profile of all your customers, everything about them in your service, and you're going to label each ones that left or not, and now you have data that's set up to answer this question. Well, you almost have it. It's probably full of errors. But. So this can be tricky, the statement of the problem. Okay, so here's another example. Let's predict the Oscars. Okay, here are the predicted winners. Okay, what is step two? Who can tell me? The history of? That's a pretty good idea. That would probably work. Yeah, this is a good idea. Okay, I'm just waiting to see if there are any other suggestions. No? Okay, so this statement, of course, is not specific enough. We know this. So what data can we collect that predicts Oscar wins? This is my idea. And there's a suggestion here to use historical information and looking at the movies that have won previously, and I'm looking at the metadata of the movies, right? Perhaps like the budget or the actors or the director and things like that. Yeah? Yep. That's a great place to start. And if you don't already know, this is something we do every year. We publish a blog post the Friday before the Oscars with our prediction for the wins. And in 2018, we actually got 6 out of 6 right. We actually got 8 out of 8 right, but we were too shy to say what we thought the other 2 would be because the probabilities were too low. And then in 2019, we cast away our shyness and made predictions even though the probabilities were relatively low. And so we only got 4 out of 8 right. If we'd stuck with our previous trend, we would have got 4 out of 4 right, but that's okay. Please be aware this is still significantly better than guessing. Okay, it's not true false, right? It's these 5 or 6 movies, which one is going to win? So the odds are actually fairly low. 4 out of 8 is not like flipping a coin. All right, it's much better than guessing. Okay, so we do this every year, and so you can read about how this is actually done. You can play with the data too. So how is this possible? And so if you think about how an Oscar is won, there's all these movies, and there's 7,000 members in this academy, and they vote, and then the vote is used. Okay, but these people that are voting are using the data you would expect, right? very similar to what you were talking about, the actors and the directors and the history of the movies and the budgets, the cost and everything else. But of course, there's also lots of bias and other things, right? Best friends and, you hate that director or whatever. There could be all kinds of things. But winning awards is not a random event. You don't just, out of nowhere win an award, right? Usually there's a history of awards, like there's this BAFTA and the Golden Globes and Directors Guild and the Writers Guild and the Lenders and Critic. And if I showed you this and said, look, The Shape of Water last year won all of these awards except that one, do you think it's going to win the Oscar? You would say, yeah. I mean, it's just the Writers Guild that like that movie better. Those guys, they don't know what they're talking about, right? And the idea here is that these events are not independent. They're similar and not identical. And are factors that contribute to each win. So you can expect a higher probability that The Shape of Water will win. And so this is exactly what we do. We take all the movie from the IMDb, and we have everything about it, right? The year, the movie, the release date, the Critics' Choice Awards, the Art Directors Guild nominated categories. It's a big, giant amount of data that you can pull pretty easily. And we do a little bit of feature engineering, too. We have to create some counts and things. And then this data set I mentioned is publicly available, so you can actually go to the BigML gallery, and you can play with this year's, too, so you can try building your own models. It's super fun if you haven't already. I know some people have built models that work better than ours. Okay, so tidbits and lessons learned about the Oscars. When you're specifying the problem, be as specific as possible. Hopefully I've drilled that in. Not let's predict the Oscars, but let's predict the Oscars by correlating a series of award wins with the final Oscar win. That's the idea. The statement of the problem will guide the data required. See, once you have this statement, you know exactly what data you need by correlating a series of award wins. Okay, I need to know all the awards that have been won. All right. Be aware of the cost of collecting the data versus the ROI. Okay, so when you go back home and you're starting to think about all the cool machine learning projects you can do, have this chart in your mind. Okay, there's the ROI, the impact and cost to your business. You save $1, you save a billion, right? And then you have the increasing availability or decreasing complexity. So down here, I have no data. Up here, I have data just lying around, or it's super easy to get. Okay, everything down here should be a no-go. The data is super hard to get, very expensive, and the ROI is a waste of time anyways. Don't do those first, okay? Everything up here, the data is easy and the ROI is low, but maybe there's something useful to do in there. That's all right. This is, the data might be hard to get, but the ROI is high, but it might be hard to solve. But maybe you want to think about it. But as your first project, you're going to start there. The very first thing you want to do is anything where you've got data is just lying around and the ROI is going to be high. That's a great place to start. A very fertile ground for thinking about your first machine learning application. Okay, so in our case, the IMDb data was readily available. So we're done, right? That's it? No. You can't escape feature engineering. Okay, we had to make all these BAFTA 1 categories, which was a list, and we had to massage the data and make it work right for us. We had to do a bunch of aggregations for the nomination and award counts. You also can't escape feature selection. We had this idea that maybe what people write in the reviews, because IMDb, people can just log in and say, I hated this movie, it was terrible. And we thought maybe that would actually affect the outcome. And so we did a bunch of text analysis on the full user reviews. It was super hard to collect all of that user review information, and then turned out to not be useful. It really didn't improve the model at all. And so that's another example of feature selection. Okay, and how were we confident in our prediction? How is it that every Friday we publish a public blog post and we feel at least reasonably confident that we won't look like total fools? Right? How do we do that? Well, we evaluate it, of course. Of course. So we have data from, let's say this was for 2018, I haven't updated it yet, but we have data and we take for 2000 and 2016, all those movies, everything I talked about, 119 different variables, and we just split it. We make this data 2000 to 2012, and we build our model off of this one, and then we use these 3 years here to make predictions about who the winners should be, and we see how well we would have done in those years. And then when we're done doing that game, we just roll this whole thing back up and use the entire data set and predict this year's. But we can see over the years how well we would have done for that next year, right? So we have sort of an idea. And when we did this, ultimately, you'll remember, use the whole data set. But in order to evaluate success, right. We built it, okay. So eventually we got this AUC of a 0.98 across all award categories, which is pretty darn good. Okay, so we felt pretty confident in this model. Okay, so the model seems okay. What next? So let's talk about effort of machine learning application a little bit. Okay, so we have stating the problem as a machine learning task. You're going to do a lot of data wrangling and data transformations and this feature engineering, modeling, evaluations, and predictions, and measure results. And what I want to tell you about is where you're going to spend your time in this process. Okay. Oh, and you're going to do it again. Okay, so stating the problem. This is harder than you might think, actually. I mean, 10% of the effort seems high. Even every time I look at the slide, I go, that seems high. But then I think about problems I've tried to do, and yeah, it's actually probably about right. It's iterative. You start down a path, and you get halfway here, and you go, well, this doesn't work at all, and you end up going all the way back up here and trying to change your problem statement a little bit. And so it is a little bit more difficult than you might originally think. Down here, this part, the part that everybody likes, playing with the models and doing the evaluations and making some predictions, it's like you spend almost no time there at all. I mean, maybe a little, okay, but overall, 5% of the effort for each one of those. And about 80% of your effort is spent in the middle there, okay, just trying to get all your data to do what you want it to do. All right, now that I've shown you this slide, please keep in mind that this part is only low because of platforms like BigML. Okay, if you were going to go home and write your own ensemble, code in, I don't know, Fortran or something, then this effort would be much larger than 5%, right? Okay, so that is part of the commoditization of machine learning. That's what I was talking about before. This part is easy now, all right? And you can well imagine that we're busy innovating here. So we actually just did a big release where you can merge data sets, and there's going to be a lot more cool stuff happening here as well, as soon as we get Ken back on that project. Okay. Reality check. I'm going to give you 3 important concepts in applying machine learning, right? So all machine learning models are wrong, at least somehow they're wrong. Real-world machine learning is iterative, and end-to-end machine learning is compositional. Now I'm going to tell you what all those all mean. Okay, let's start here. End-to-end machine learning is compositional. So these real-world problems I'm talking about, like these examples I gave you, NDA-Lin and pre-series and everything else, they're solved by applying a combination of algorithms. You don't just do that workflow I showed you, build one model, and then you're done. Okay, it's rare. Very rarely is it one and done. See, I'm ahead of my slide. So here's a basic workflow. This is, you create the source, data set, model, prediction. We saw Charlie doing a little bit of this. And, excuse me. But maybe you need to do some feature engineering, right? So you're going to take some data set of homes, and you're going to do some filtering, create new features, and build a model. Excuse me again. And now you're going to look at all the homes that are for sale on the market, do the same filtering, create new features, do some kind of a batch prediction, create a data set. And the end result is you're going to do this to analyze the housing market and look for houses that are too cheap or too expensive. Okay, but you can see it's much more complicated than just build a model, right? There's all of this data transformations happening and scoring. And even at the end here, what came out of the scoring algorithm still wasn't what I wanted because, for example, this data set in my mind, I've done this project, is predicting what the sale price should be on the market, and then you have to compare it to what the actual asking price is so that you can find the deals. So you still have to do one more step of subtracting all these numbers. Okay, so you're not done even at the prediction stage. Okay, it's a simple example of compositional. So each of those steps in a workflow like that can be multi-stage as well. You might need to do filtering and cleaning. Okay, so here's a workflow just to filter your data set. So here I've got some data set that I'm creating. You'll see this one, diabetes data set. And I split it, I do a training and test set, and I build some kind of anomaly detector. I use the anomaly detector to filter out all the patients that are anomalous. Okay, and I have a nice clean data set, and I build a model there. And maybe I take the test set and I run it through the all model, and I compare those evaluations and see whether or not removing the anomalous patients improves the outcome of my model. Okay? All right, and if this works, then this is going to be my workflow. I'm going to have to do this anomaly detector every time, that whole workflow through there. Okay, and we have tools to make these workflows easier too. That's a little tease for the WizML stuff that you'll see tomorrow. Okay, you can fix missing values. I guarantee your data set will have these. There's lots of ways you can do this programmatically. You can use machine learning to replace missing values, and so this would be a workflow that does that, right? So we take out some zeros that were actually supposed to be missing values, we remove them, we try to build a model that predicts what those missing values should have been, and we put them back in, and we create a new data set out in the output that's nice and clean. All right? But again, this is just preparation. The output here is a fixed data set that I'm then going to go on and build my actual model with. Right, so this is big, long workflow. Lots of steps. You might need to tune a model for optimum performance, right? I might try different size ensembles and see which one works best. Or you could use OptiML or something, but maybe you want to do this by hand. All right, so you could have a workflow that is doing some kind of optimization process, is what this is meant to allude to. You might need to find the best features. There's lots of algorithms for doing that. This is the whole idea here. The game you're playing with machine learning is, I'm going to start with 1,000 features, and we do have customers that have data sets that large, actually some that are much larger. Machine learning is going to just be able to build a model from those 1,000 features that works, which a human wouldn't be able to do efficiently, right? It's too many things to think about. But at the end of the day, it turns out there's only 10 or 12 features in there that are really important. The other 900 are just, perfunctory. They don't do much. And so feature selection is a very powerful way to reduce that complexity, right? Improve the quality of the model. Sometimes those extra features are just adding noise. You might require separate models for different domains of knowledge, okay? Multiple training and scoring. All right, so if I want to build some kind of a fraud detection system, I might be taking my transactions, and I've got a data set where the transactions are aggregated by the card, the actual card you're using. They're aggregated by the user, so this is transactions that user performed across all accounts, every account, all their cards and everything. And I might have another one that's a data set aggregated by profile. Are you a student? Are you a retiree? What is your profile? And I want to look at transactions aggregated by that. And I build different kinds of anomaly detectors. Is this anomalous for your card? Is this anomalous for you? Is this anomalous for your profile? And then I compute an anomaly score for all of those, and I combine take a new transaction and I score all of those anomalies, and then combine those scores and do a final approval, yes or no. Maybe, it could be whatever metric. Maybe it's as long as you're okay in 2 out of 3 of these, everything's good. Or maybe it has to be all 3. That's irrelevant to the point that you might have a system where you're combining lots of models in this way to get the outcome you want. Okay, so even after you deploy the model, your model's in production, it's making predictions, you're going to need some kind of a workflow to monitor performance to know when to retrain. Okay, the data's changing all the time. I like to say your data has a time value to it. All right, the data from a year ago in most domains is not as valuable as the data you just collected. All right, there's some domains that don't change very often, but there's quite a few that change all the time. And so here's a workflow that does that. You might have your training, you build your model, an anomaly detector, and every time you make a prediction, you see what the anomaly score of this input data is. And if it's very anomalous, that means it doesn't match your training data anymore. And so you trigger a little process that sends those points back into your training set, and you retrain. Okay, 3 important concepts. So all machine learning models are wrong, that's okay, but some are useful. Better features always beat better algorithms. I'm just giving you tenets now. You'll have to take me on faith for this. Okay, it's always better to spend your time on the actual quality of your data than it is to worry about which algorithm you're going to use, especially because which algorithm you're going to use can be optimized away with automated machine learning. So good algorithms exist and are already good enough. Don't worry about writing your own. Okay, you don't have to invent a new algorithm. It's okay, there's lots of really good ones. And then there's tools like OptiML which can help you optimize this performance. Okay, and the data is never good enough. It's always bad. Okay, automation is better than hand tuning, right? So this real world machine learning is iterative. If you can automate it, that's a total win, all right? You're gonna be able to take advantage of new data every day when it's coming in and retrain your model and have the best model all the time. That's a really great idea, and you don't want to do that by hand. You gotta have an API to do that. When your data is changing quickly, training speed is more important than accuracy. Okay? If your data is changing all the time, you need to be able to train very quickly. And repeatability, I would say, is superior to a single strong result. Okay? If you build a super great model, but tomorrow you can't, that's harder to argue for the utility of it. Okay? Because your data does have this time value to it. And then the compositional side, your problems are going to be solved with a workflow algorithms. Machine learning solution is not real until it's in production. It's nice to talk about, but until it's actually making predictions somewhere, it's not in production. And machine learning is here. We just need like 100,000 times more people actually doing it. Yep. Look at that, right in time. I might have rushed a little, but that's okay.